Okay. Let's see. Okay. Always something. Okay. Right. Okay. So actually, tell me your name. Ellen Clardy. Okay, got it. Wrong date. Let's go over here. Okay, got it. Okay. So any questions from last time? Yes? Yes, highest. So if you try a few times, I'll just take the highest one. Yeah. Other questions? No? Okay. So let's see, today we will, quick review, last sort of call on the cost volume profit framework. And then we'll be doing much more with the time value of money. Finish off some stuff with future value, FV, and then talk about the present value, PV, and then we'll talk a little bit more about compounding. Okay? So we want to think more about frameworks. You know, sometimes it's possible to have a problem that involves some type of a description of a business problem or, you know, real world problem. And then it's possible sometimes to solve it directly, right? Like you might say, you know, you can sort of intuitively feel maybe fixed costs are different from variable costs. If we add all those together, you know, then there's a price. And then if we subtract the variable costs from the price, then we divide them, we should be able to get this QBE. And so, but why is that correct? You might not be so confident. And so it turns out that if we have this more structured approach, more structured framework, then you can be sure that the calculation you did gives you what you think it does, but also it's broader and can handle more cases and is more general. And so here's an example that we looked at before. And, you know, the first thing that you do is, you know, like on a quiz, say, or something like that, you have to read a problem. And then, you know, by then we'll have looked at future value, we'll have looked at present value, we'll looked at annuities tomorrow or next class. And then when you read a problem, you have to identify it first. That's the first thing. You have to peg it. What am I looking for? And so if you read this problem, you spot it as a CVP problem, a cost volume profit problem, you'll think, okay, maybe you think this is what I need, or you think of the worksheet on the calculator and know that, okay, I remember I need the fixed cost, the variable cost, the price, and then maybe the net income, right? But you have to figure out what information do I need, and then you have to go get that information. Okay, and then once you gather all the information, then you can go ahead and apply the analysis and solve the problem. Okay, so first thing you do is you spot it as a CVP problem. So at the moment, or that this, sort of now we don't have too many frameworks, and so it's pretty easy. It's not present value, right? It's not future value. So it's a CVP problem. So then you think, okay, this is where we're going, and now we have to get the costs, or get the information, right? So if you look at the information, right, step 2, you might say, this first one is Q, right? Cost of deliveries, we kind of already talked about that. That would be a variable cost. This cost of gas, right? It kind of does change. So it's not fixed, right? But the question is it variable or is it mixed, right? So it turns out we know that this is mixed. And then the last one, as the volume of business, as the output, as the Q, changes, it doesn't change, right? So this one is clearly the fixed cost. Right? So that's sort of step 2. You want to classify the costs kind of this way. And then step 3, if there are mixed costs, and clearly we have a mixed cost here, then we have to separate the mixed cost into the variable components and the fixed components, right? So basically the way that you do that is you find a line through the data points. Here there's only 2, so you just do sort of find the slope, plug in for the slope and to the equation, and you find the fixed cost. So now you have that the cost of gas is this 0.5, half a dollar per delivery plus 15. Okay, so now this is your mixed cost. Okay. So then remember that where we're going is we need all the fixed costs, right? This little subscript T there is fixed cost total. So you need all the fixed costs, the total fixed cost. This VC variable cost, the subscript T here again is total. So you need all of the variable costs in order to get the good estimate for the break-even quantity or the target income quantity. If you have, if you say we want to make $5,000, so you obviously, in order to have a net income of $5,000, you have to cover all of your fixed costs and earn $5,000 more. So this numerator would be larger, and so your QBE, your quantity would be larger, right? But here we just want the break-even. Okay. So once you separate it, then you have all of the fixed costs. So the fixed cost includes the fixed cost from gas and the lease, which is 65, so you get a total of 80. The variable costs have this variable cost of 250 plus from the mixed cost that's been separated into the intercept B and the slope M, say, the variable cost for the gas. So you add all of those up, and finally you have your total fixed cost, your total variable cost, your price, and then here and net income is 0. And so we're using this special case. So this is the more general case. We're using this special case, and you can either plug it into the formula or use the calculator on the worksheets. Okay, so where does this come from? Sort of, in college, you want to sort of question the assumptions. Okay, so we're really relying on this. Where did it come from? So we're going to go through a little bit of a derivation here. And so, this is an applied math class. So we don't have to concentrate so much on the derivation. So, don't get hung up on the derivation. On the other hand, this is a math class, and part of math is about sort of proving things and demonstrating things. So this is just sort of a little proof. And so, where does this formula come from? And so I think of the origin of this formula is kind of a tale of 2 lines, right? And so we start with the revenue line, which is simply price times quantity, right? What's the price? How many did you sell? Multiply those together. That's the money that came in. And the money that comes in from sales activities, service activities, sales activities, the money comes in, that's your revenue. Okay. So then we have the total cost line. And again, variable costs, you add them all up. Fixed costs, you add them all up. Don't forget about the mixed costs. Mixed costs, see the formula doesn't have mixed costs. So you have to take mixed costs and separate them into the variable component and the fixed component, and then put all the fixed stuff together and put all of the variable stuff together. So this total cost line is modeled this way. Sometimes people call this the cost structure. Okay, so if you ever hear people talking about the cost structure of the business, that basically means the variable costs versus the fixed cost. And we're not going to go into this, but the cost volume profit is a big topic in accounting and management accounting. And so you can use this to help you understand, certain businesses have more fixed costs, right? And they have less variable costs. So what are the consequences of businesses that are structured that way? And on the other hand, some businesses have a big variable cost, and smaller fixed costs. And so those businesses are that rely more on variable costs have a slightly different structure. And so if we went on studying cost, volume, profit, we would start to look at some of those types of structures of businesses. But we're actually just using the cost, volume, profit stuff kind of as a warm-up because of math and because it's just, lines, and lines are fairly simple. Okay, so those are the two lines. So really the starting point for where this comes from is the expression for net income or net loss, right? What is net income? You simply take the revenue minus the costs. And so actually once you have this, we're basically done, right? So here, instead of doing this NI parentheses L for net income or loss, we'll just simplify that to NI for net income. And then we take for revenue, we plug in the line or the equation for the revenue. For total costs, we plug in the equation for total costs, right? So then we either distribute the minus sign or open the parentheses or bracket, however you want to think about it. And then we simply move this fixed cost over to the other side. And then also at the same time, notice that you have these two things, price times the total variable costs, they're multiplied by Q. We can factor that out. Okay, once we factor that out, we can just divide by that. And then we're basically done. And then once we set the net income equal to 0, we have sort of the special point, special case, right? The special point. And so I think that this is a very, very simple model of a business, right? And you can see that the costs start out with the total fixed costs like rent, insurance premium, certain salaries, certain commitments that you have that the firm has that are fixed, and the costs, the variable, based on those fixed costs, every time you sell another item or provide another service, you have some variable costs associated with that. So your total cost line, total costs kind of creep up. On the other hand, every time you sell a product, deliver a service, sell a product, you have an incremental increase in your revenue, right? And so as your revenue grows, you could become profitable. You hopefully want to become profitable. But this also shows, that when businesses start out in the startup phase, they have, large fixed costs and they have no revenue or very little revenue. They're creating their product, figuring out their service offering, getting the secret sauce ironed out. And so their volume of business is very low. And so they can expect losses for, some time, quite some time sometimes. And then you want to sort of cross this chasm and go to the section of being profitable. And obviously, the more you sell, the more profit that you can look forward to. And then, of course, there's this one special case, which is the break-even point. And it's actually an important part in decision making, right? You want to know how many units do we need to sell, or how much, services do we need to deliver in order to become profitable, and then the whole firm has to be capable, has to have the capacity to do that. What if you do this and you find out that, you need to sell 200 items? Well, if you're sort of making those on your tabletop by yourself, you have to scratch your head and say, maybe I need to pay somebody to help me so it can, make more of these so that we can actually break even. Okay? So that's kind of CVP. Next, another big framework that we'll be looking at is time value of money. And so we started that last time. And, we asked the question, what would you like, $100 today? Oh, sorry, I should close this bracket off over there. $100 today, or some future value 1 year from now, whether it's a different amount. And so it turns out, so one of the purposes of that was to show you that kind of everybody has their own interest rate. And if the problem doesn't come out and say what the interest rate is, people will use their own interest rate and you can get different answers. And so actually, if this ever happens to you again, somebody should raise their hand and say, hey, professor, what interest rate should we use? And so just remember that these time value of money problems always involve interest rates. Okay, so we started to look at this a little bit, right? And so, and one of the tools, one of the ways that can help you analyze these time value of money problems is something as simple as a cash flow diagram. And so here's a cash flow, two main cash flow diagrams, right? One that shows that you get $100 today. At time equals 0, you have $100 today. Or at time equal 1 year from now, you would get $102. Okay, and so we mentioned that $100 today is very different from $102 some amount in the future. And so the question is, how can you compare them, right? And so what you do is you use the interest rate, right? And so you can imagine, say, instead of taking the $100 today and depositing it in a bank, right? And so if the bank pays 5% interest, then in the future, you have $105, right? And then now you have this $105 at time equal 1, and then you can do this comparison, right? And you can say, oh, clearly, I would prefer the 105. And so as long as 5% is the rate that everyone should be using, I would prefer 105%, and so I'm going to stick with $100 today, right? So choose 100 today. Okay, so obviously it's if you just do 1 year, it's very simple, but what we want to start to do is we want to start to understand that there really are 6 variables. Just like when we were doing the CVP problem, in order to answer the question, you really need to have 3 or 4 specific pieces of information, like all the fixed costs, total variable cost of price, and then if you're doing break even, net income is equal to 0. So these are the pieces of information that you need. In order to solve a time value of money problem, you really need 6 pieces of information. Okay, you need to know the compounding, and so here we're just getting started, kind of training wheels sort of a thing, and so we're doing annual compounding. Okay, so we set that equal to 1, and so in an annual period there's 1 compounding period, so that's annual compounding, and that's that's where you get started. So then there's a number of time periods. Like here it's only 1 year, but it could be 3 years, 5 years, more years, right? So how many time periods are involved? What's the interest rate? Okay, then there's typically there's a present value. It doesn't have to be present value, but usually there's some kind of a present value. And then we talked about this as being the annuity, which we haven't done, and so you could turn that off, say, and set it equal to 0. And then what you want to do is you want to determine the future value. And so we went through that quickly on the calculator. In a certain sense, so really what happened was, in order to find the future value, you say deposit your $100 in the bank, and so a year from now, you deposit it so you get it back. But in addition to getting your original deposit back, your original principal back, you get some interest, right? And so again, here you can see there's 100 there, and there's 100 multiplied by the interest rate, and so you could factor out the 100, and so you have this, factor of 1.05 times 100. Okay, and so you can kind of think of this as a compounding factor. And if you have like $100 at time equals 0, if you multiply it by this compounding factor, you kind of move the cash flow 1 time period forward. And so as we'll see, if you want to move it a second time period, or 2 years out, 3 years out, you can actually just multiply it by this factor. Okay, and so sometimes you may have learned that in earlier classes. But before we go on from that, let's kind of return back to the scenario C, where you have $100 today versus, and the choice was $105 in the future. And so now, with the 5% valuation rate, it turns out that you're indifferent. So what that means that it doesn't matter. So you see, if you apply that analysis that we did before, you come out with 105 in the future. At time, both, you know, the $100 today actually is equivalent to 105 in the future, but that's the other choice. And so that's why you're indifferent in that scenario, right? The other scenario was $100 today versus $110 in the future, right? And so, you know, it's the same 5%, it's the same $100, it's the same 5%. And so, you know, depositing $100 in the bank at 5% interest would give you 105 in the future. Now you can compare them. This time, you would prefer the 110. Okay, and so at 5%, prefer to wait. Right, instead of taking the $100 today, if the valuation rate is 5%, you would prefer to wait a year and come back and take receive 110 in the future. Okay, and let's see. So there's we kind of did this quickly on the calculator on Excel. There is a function called FV. So equal FV, future value, and for whatever reason, Microsoft decided that they would put the rate first, opposite to the Texas Instrument calculator. They put the rate first, and then they will put the number of periods. So you just have to remember to flip that around. And oh, by the way, and then it's asking for the annuity amount, because when you do time value of money problems, there's a possibility of an annuity. And so we set that equal to 0 in our cases. And then here, when you see the formulas in Excel, there's a bracket there. Does anyone know what the bracket means? So if you notice, the rate, end period, the first three do not have the little bracket, but the last two have the bracket. Okay. What that means is that those values are optional. Okay, so in order for the function to calculate something, you must put in these three values. Okay, so you must put in these three values. The other values are optional. Okay, and so in this case, we do have a present value, and we want to put in 100. Okay, so notice that if you put in plus 100, you get back minus 105. On the other hand, if you put in minus 100, you get back plus 105. Okay, so what's going on, right? If your present value is negative, that kind of feels like you're paying it out, right? So that would be our perspective depositing it to a bank. Okay, so if you put in the minus for the present value, in the future, you're going to receive 105. Okay, so who took your $100 when you deposit? The bank, right? So from the bank's perspective, what's the bank's perspective? The bank's perspective is the present value. Now we receive $100, and then a year later we pay $105. Does that make sense? So the perspective, I mean, the time value of money is sort of symmetric, right? When one person has a present value that's negative, that means they drop it off, they deposit it, they part with it, they send it to another entity, and then the future value, they expect to get it back with interest, right? On the other hand, the bank is plus 100. The present value for the bank is plus. So they are receiving $100 now, and then they're not just going to, keep it, right? Somebody deposited with them. Why? Because in the future, that person, they want it back. So the bank has got to pay it back. In the bank's future value is the other side of the transaction, is that the bank will receive the present value and the bank will pay. Okay, so it kind of like numerically, 100, 100, 105, 105, it doesn't matter. But you should just keep in the back of your mind that the sign, the plus minus matters a little bit. But as long as you're consistent, you won't be confused. Okay, does that make sense? Okay. And so then another method, traditionally favored in accounting and accounting classes, is these tables with these factors. And so, here it's pretty clear at 5%, it's just 1.05, 1.06, 1.07, 1.08. And then what happens is 2 years out, you get these. This is actually just this one squared. So for example, this one is actually 1.05 squared. So this whole line, a line in the table, this entire line in the table, is just the upper one squared. And so, for example, this one is 1.08 squared. Let me see. So if I, oh no, let me grab this one. If I launch my calculator, we could just do 1.08 squared. Maybe we'll do that later. Okay. So here's just a couple of sample problems involving more than one time period, right? So suppose Malia deposits 2,000 in a CD that earns 6% compounded annually. So still keep it simple. How much will she have after 2 years, after 3 years, after 10 years? Okay. So when we get started with these time value of money problems, really, I think the best starting point is to draw out the information that you need. N, I, PV, PMT, and FV. And here, when it says, so always, the first row of this table always is sort of the annual compounding. So this one means annual compounding. Okay. And so the first question is, well, how much will she have after 2 years, right? And the interest rate is 6%. And now she deposits, 2,000 in her certificate. How much, will she have after so many years, right? So the question is really asking about the future value. And again, oops. PMT was a little messy last time. PMT. Okay, 0. Okay, and so clearly the present value, if you really want to be correct, you might say negative 2,000 because she's depositing it, but you don't, whether it's plus or minus doesn't really matter too much. Okay, and so you could just pop these into the calculator, right? And so on the financial calculator, what you do is you want to clear TVM. So right above FV, there's clear TVM. So that's up above. So you do second, and then clear TVM. And then you just basically march in a row. So here you do 2, and then N. And so that sort of confirms that you've entered N is equal to 2. For I, you just put in 6. Right, and then for the present value, PV, we put in 2,000. And then we can do this plus minus if you want to. It's just toggles, so on and off, on and off. So if it's minus and you hit it, it makes it plus. If it's plus and you hit it or tap it, it makes it minus. Okay. PMT is, oh, sorry, we have to put that into PV. So now we have that the PV is entered. By doing the second clear, we put 0 into the PMT value, but if we want to see that, we can type recall PMT, and we can see that indeed PMT is 0. Actually, if you want, you can do recall FV, and the FV is equal to 0 at the moment because it was cleared. And so we can say compute FV, and then we see that the FV is 2247.20. So that's 2247.20. Okay, and then if you forgot, oh wow, what did I put in for n? I forgot. Again, you could just push recall 1. You can see, oh yes, that's that value. And so if you want to see what you put in for the interest rate, you just recall first and then the interest rate. And then if you want to see, oh, what was that future value again? And then again, you see the asterisk, which means that this is the value that was computed in that set. Okay, so, you know, sort of the kind of long way, right? So year 1, you would have 2,000 plus 6% of 2,000, right? So that's equal to 2,000 plus 12? No, 120, I think. Right, so this would equal 2,120, right? And so if we wanted to do this on the calculator quickly, we would just say put 1 into n and then recompute the future value. And so I left the 6% in there, and I left, recall, so I left the 6% in there, and recall PV. I left the 2,000 in there, and all I did was change the 2 into 1, and then I just recomputed the future value, and so that's the amount after 1 year. Okay, so at year 2, what happens? Now you start out with the 2,120, and then you have to have the 6% of 2,120, right? So now you can actually factor out the 1.6, say. So if we factor out 1 plus this, I'll just do 0.06 times 2120, right? So here, what we do is we factor out the 2,000. So we notice that there's a 2,120 here, there's 2,120 there, right? So we'll factor out the 2,120, and so this is obviously 1, right? You can go backwards and say 2,120 times 1 is 2,120, and then 2,120 times this 0.06 will be this 6%. And so what I did in going from here to here is I changed the percentage to the decimal, 0.06. Okay, so now what I can do is I can say that this is 1.06, right? And now this 2,120 is actually 1.06 times 2,000, right? Because that's what this is, right? This is really equal to 1.06 times 2,000, the present value, right? And so clearly when we do that, we have that this is 1.06 squared times 2,000. But remember, 2,000 is our present value, so we have 1.06 squared, 1.06 squared times present value. Okay, so that's how kind of for year 2, there's this compounding factor that's squared. Does that make sense? Okay, so maybe you've seen this before. And so really, right, year n, you just take the FV is FV for year, the FV for year n, right, is simply this 1.06 to the nth power times the present value. And oh, by the way, this is the interest rate. So kind of in general, right, you have FVN is equal to 1 plus I to the n times the present value. Does that make sense? So maybe some of you have seen this before, but this is sort of the basic idea. Right? So then anyway, 3 years, 10 years, it's really, you know, say for 3 years, what's FV3? 1.06 times what? 1.06 to what power? 3, right? 3 times the present value of 2,000. Right, so if we wanted to do that, let me see, go back to the starting point here. So if we wanted to compute this out sort of the long way, we would do 1.06, and then we do y to the x 3 equals. So now we have this factor, okay, and then we multiply it by 2,000, and we get 2382.03. So 2382.03. Okay, and so if we wanted to do this with the registers, right, the interest rate is the same, the present value is the same, but we have to change n to 3, right? So we just put 3 and pop that in there, and then when we compute the future value, we actually get the same thing. Does that make sense? Yeah. And then Excel, same thing, you know, except that you have to remember that you put the interest rate first, use the FV function. So Excel would be equal FV. You put the, in Excel, you could either say put 6%, or you can actually put 0.06. Excel will work with either the percent, but you have to put in the, like 6%, you have to put in the percent, or you can do decimal, 0.06. So Excel will work with either of those in the first position for the rate. Okay, and then clearly n would be 3, the annuity amount in this case would be 0, and then you could either put in, you know, plus or minus 2,000, right? Sorry, don't put in the comma, right? Don't put in the comma. Why? If you put in the comma, Excel will think that you're putting in the comma and that you've put in a present value of 2, and then this 000 would be the next. Does that make sense? Okay, so if you ever are entering like these large numbers directly into a formula, which sometimes people actually prefer not to do, you know, sometimes actually what people will do is they'll actually just drop this into some cells on an Excel table, like literally C, N, I, you know, PV, and then over here they'll say equal FV, and then they'll refer to this cell or refer to this one for the interest rate, refer to that one for the N, and refer to that one, and that, so that way you don't have this possible mistake of putting in a comma into the Excel function. Okay. So you do have to be careful with that. Also, you know, if you want to know, if you see this number, you know, what are the inputs to that number? Well, you know, you just click on it in Excel and then the formula will show up. But if you actually have the values on the sheet, then you can just look at the values on the sheet, and then you know that, oh, this computed cell, you know, this computed cell came from, you know, obviously it would be 3, you know, then you don't have to like click on it and look at the formula, right? It can be a little bit clearer. Okay, and then the last one, 10 years, right? So that would be, say, FV10 is equal to 1.06 to the 10th power times 2,000. Okay, and so we could do that. move my calculator over there. 1.06 y to the x 10 equal times 2000. It's kind of a few steps to take. 3581.60 or 0.70. 3581.70. Something like that, right? Oh, come on. Okay, anyway, let's see. While it's catching up. So to get 10 for 10 years, we can simply put the 10 into n, right? And then recall that we still have the 6% in there, recall that we still have the PV in there, recall that there's no more annuity, and we calculate the FV, and we got that. Right? Yeah. Okay. So that's kind of future value. When a trust matures in 5 years, Keikoa will receive 10,000. If the market rate of interest is 6%, how much is that worth now? Right? So again, it's a spot this. My first thing, this is not a CVP problem, right? This is a TVM problem. Okay, so TVM problem, right? C, N, I, PV, PMT, and FV, right? When a trust matures in 5 years, that's the future value, right? Keikoa will receive 10,000. Oh, whoops. Okay. If the market rate of interest is, so actually we might as well say 5 years. Oh yeah, and then when you start out with the TVM table, the first row is always 1. So here we're talking about 5 years. And the market rate of interest is 6%. Okay, how much is that worth now? So that's clearly PV, and then there's no mention of these ongoing annuity payments, so that's off. So now you can actually go ahead and solve the problem. And so this is actually a PV problem. So we'll come back maybe. Okay, so now we want to look at present value. So if we return to that example before of comparing $100 today to $102 in the future, right? We already showed how to move, use the compounding factor basically to move this forward, and then we can compare these two, and then we can say, well, 105 is greater than 102, so this is what we should prefer, so we don't want to wait. At 5% interest, we would rather take the $100 today. Okay. So if you kind of step back and look at this, you might say, it looks like there's something missing, right? Here's a little cash flow diagram, here's a little cash flow diagram, here's a little cash flow diagram, but what about over there, right? It's a puka. It's this opening. It's an empty space. So you might think, what if we put in a cash flow diagram over there? But what would this cash flow diagram be, right? So on the one hand, we moved this cash flow forward to the future, and we computed the future value, right? Here we have this other value, 102 value that's in the future, right? So we could imagine that we put in this 102, right? And if we put in a future value, what would we expect to get back? We'd expect to get back the present value, right? The PV. Okay. So how did we go from here to here, right? Basically, we multiplied by this 1.05, right, times 100. Right, so this was our PV. This was our factor, right? Yeah, so to get the FV after 1 year, we took the PV basically, and we multiplied by the 1.05. So if you start with the PV and you multiply by 1.05 to get the future value, if you start with the future value, right, and you know the interest rate is 1.05 and you want to get the present value, what do you think you do? Any takers? Right, so here we started with the present value. We took this 100, say, well, what if we took this 100, we could deposit it in a bank, and then at 5% interest, 1 year later, we'd have 5%. And so how do you get that? Well, you start with this present value, you multiply it by this compounding factor, and then you get the future value. Now, if we want to start with the future value, so if multiplying by the present value, if taking the present value and multiplying it by 1.05, this factor gives you the future value. What happens if you start with the future value? How could you get the present value? Divide, right? Yeah, exactly. Okay, except, there's always an except, right? I can do it this way. Oh, I can do it this way. Except, to go backwards, right? We could say that the PV, right, is equal to it is of course equal to 105 divided by 102. 102 divided by 1.05, right? Okay, but it turns out that what we usually do is say we multiply by this 1.05 times 102. So, I mean, it's kind of like splitting hairs, but instead of dividing by this factor, people would actually rather multiply by things, right? I think people just prefer to multiply. So we actually take the reciprocal of that factor. And sometimes people, if you divide by, 1 over 1 something greater than 1, sometimes people call this a discount factor. Okay, so maybe to go forward, you multiply by the compounding factor. So to start with the present value and to take it to a future value, you multiply by the compounding factor. You could say, well, if we want to start with a future value, so this is basically an FV, we could divide by this, say 1.05. We could start with a future value and divide by the compounding factor, but instead of dividing by the compounding factor or saying that we divide by the compounding factor, people would take the reciprocal of the compounding factor and have the discount factor, and we multiply by the discount factor. Okay, so actually, what could we do? We simply take this 102 and divide it by 1.05, or multiply by the reciprocal. We get 97.14. So 97.14. Okay, and so now instead of comparing, out here, we are comparing here. Okay, and 100, is larger, and so we would prefer this case. Right. So notice that if you're comparing at time equal 1. You're comparing 105 to 102, and clearly you prefer 102, which is the first scenario. If you take the 102 and sort of discount it back to time equals 0, you're comparing 100 versus 97. Clearly 100 is larger than 97, so you prefer this case. So whether you do the future value comparison or the present value comparison, you still arrive at the same case, right? Same conclusion, but the numbers are clearly different because you're looking at future value versus the present value. Okay? Sorry? Comparatively, they're the same, right? Except that here we're looking at time 0, and here we're looking at time 1. So yes, they are comparatively the same, but they're in different time periods, and so that's why the numerical value is different, because a cash flow at time equals 0 is different from a cash flow at time equal 1. Because of interest rates, they're equivalent, right? But they're different. Okay, they're similar, they're related. And so clearly with the TVM registers, right, here we want, what do we have in there? We have, 10. Oh, wait, we just did the 10-year thing. Okay, so actually we're doing a new problem. So the best thing to do would be to clear the TVM registers, which is up there. So you do second, clear TVM. Here we're just doing 1 year, right? Our interest rate is 5%. Okay, this time we want to compute the present value. So let's just do 102 and the future value. And we did clear everything, but we could just check, make sure that the annuity value is off. Now, this time we want to compute the present value. Oh, wait, what? Sorry. Sorry. 102, I think, was the future value. And then what did I put in for the interest rate? I put in 5%, right? So now we want to compute the present value. There we go. 97.14, right? So again, just check, right? I put in a 1, right? I put in a 5%. I put, this is what I computed. Want to make sure that there's no annuity value. And then I had put in 102. Okay, so now got the PV. Okay, so it's a little bit faster if because you can just focus on inputting the values. You don't have to key things in and y to the x equal exponent and then multiply, right? You just put them in and then compute the answer. And so again, in the business finance class, the focus will be on the decision making. So you have this project and you have that project and some other project. Which one do you decide? And so the mechanics of actually computing the present value or the future value or the annuity values, the mechanics of computing that, you sort of assume that you know that. So in a math class, you sort of want to learn the relationships and exponents and things like that. And so in a math class, it is important to see the formula and sort of develop an understanding and intuition. However, when you get into a finance class, the focus is not on computing the answer. The focus is, okay, we know how to get the right answers for several projects. Let's compare them because we want to make a decision in business. Okay, so that's why you want to really, really get this so that you can be fast and efficient. Okay, and also when you do the Excel cases in those classes, you want to use these basic time value of money functions and then some of the other functions that you'll learn about in those classes. So basically, this is kind of like running through the whole thing, where you could clear TVM registers or not. It's good practice to do. So you just put in 1, and you can check, and then put in those numbers, or compute it this way, or do it with the present value. Oh, and then here I'm illustrating that you could either put in, here the sort of the main illustration is whether you do plus or minus. But then also showing that you can put in the decimal value of the percent of the interest rate or the percentage value. But if you do 5, you have to put in percent. Okay, otherwise it's going to be like 500% if you just put in 5, right? So the percent makes it that decimal. Okay, and so here we're using the PV function, but the PV function is basically the same order as the FV function, except obviously where the FV function had PV over there, the PV function has FV over there. Okay, and then here are what are known as the discount factors, you can see that if we took the this one point, or we can take the 1.05, and then if we take the reciprocal of that, we get this 0.95249538. So these guys here in the table of present values are just the reciprocals of the future values. Okay, and so you know, how would you do that? You know, if you had to do like a table problem for this one, again, you know, you always do the C. The C is equal to 1 and N, I, PV, PMT, then FV, right? So here the FV would be, say, 102. PMT is off. This is what we're trying to calculate. Our interest rate is 5%, and we're doing one time period. And so when you use the tables, you actually focus on those, right? So you do N is 1 and I is 5%. So you would be using this value, 0.95238. So then you just take this 0.95238, and so really, you know, what is this? This is really 1 over 1.05 times this PV, sorry, FV, because we're discounting, right, FV. And that's how you do that. So you would basically just, on your calculator, take this from the table, 0.95238, and then multiply it by 102, not 12, 102, and then you get this same 97.14. Okay, so those, and so if you start with the information from this TVM data frame, whether you're using the tables, you use this information, whether you use the calculator, right? You put these numbers into the registers on the calculator, and also if you're doing the Excel function, you put these same numbers into the Excel function. Okay, so that's why it's good to do it this way. Okay, questions so far? No? Okay, so now we want to continue in TVM stuff, and we want to understand this idea about compounding. Okay, basically when the compounding is less than 1 year. Okay, and so you may have heard this idea that the compounding is interest on interest, right? So you earn interest on interest. So basically, interest is awarded and posted, and then you can earn more interest. So let's see what this is what's going on. Okay, so let's consider an environment where there's 6% interest. Okay, so you deposit some money, say some amount in the beginning, and at 6%, you would expect that a year from now, you would get the amount back with interest. What happens if you don't make it to the end of the year? What happens, halfway through, after 6 months, you say, well, I don't want to wait to the end, but after 6 months, how much interest have you earned? Right? The deal is 6% annual interest, right? And so you wait the whole year, and then at the end, you get your 6% interest. Okay? So halfway through the year, you have not earned the whole 6% interest, right? Because you haven't made it that far, right? So if we sort of stop or temporarily halt at the moment halfway through, you've only earned half the interest, right? So that's 3% after 6 months. Okay. Now, if you award and post the interest and basically put the interest in the account at that point, and then let it ride for another 6 months, the balance of the year, right? Well, what's going to happen? Well, now, midway through, you don't have 100 only anymore. You have 103, right? So you expect that 103 back from mid-year, but you expect interest on interest, right? So by the end of the year, you will, if the interest is 6% compounded semi-annually, you will actually have an additional 9 cents interest, right? And where is the 9 cents from? 9 cents is from interest on interest, right? The 9% is because of the semi-annual compounding. It's because of this interest. So here's the interest, right? And then this extra 9 cents, that's the interest on interest. Does that make sense? Okay. So basically, when we go from the annual compounding and we go to the semi-annual compounding, the interest rate is halved. Why? Because it's semi-annual compounding, and so we're compounding sort of halfway through. But we also have 2 semi-annual periods, right? It's not just the one annual 6%. It's, we split it up into half the period is half the interest, and then the other half the period is the other half of the interest, right? And so that's why we square it, okay? And so what about quarterly? Well, it's more confusing, but after 3 months, quarter of the year, you have only earned, you know, a quarter of the interest. So here's half, so half of a half is 1.5%. So you've only earned 1.5% after a quarter of the year, so that's only $1.50, right? But then you have a second period to go, and then a third period to go, and then a fourth period to go, and you earn interest on interest on interest on interest on interest on interest. And so in the end, the net is that at the end of the year, you have an extra 14 cents from the quarterly compounding. Okay? And same thing with monthly, except I didn't do monthly because it's just too small, right? So what's going on, right? Basically, I didn't write the diagram for monthly, right? But basically, the common compounding periods are annual, which you don't see too much because it's too simple, and it's more realistic to have, you know, monthly or semi-annual compounding, sometimes quarterly also. But basically, when we build out our TVM data table, what we need to do for semi-annual compounding, we need to take, n, and multiply it by this 2, the number of compounding periods, and then we have to take the interest rate and we have to divide it by 2. Okay? And so this is really what's going on. And for quarterly, again, now 1 year is not 1 period anymore, but there are 4 quarterly periods. Okay, so the number of compounding periods goes to 4, right? Because in 1 year, quarterly compounding, there's 4 compounding periods. There's 4 compounding periods, right? Because after 1 quarter, you're gonna award the interest and basically post it into the account. And then in the next quarterly period, you're not starting with only 100 anymore. You're starting with $1.50. Okay, so then this next compounding period, you have that. Then you're going to award interest on all of that, and then now you're starting out with 100, maybe $2.05 or something like that. No, it was $103 and $132. Anyway, right. So then anyway, you get the idea, right? So quarterly compounding, there's now 4 periods in 1 year, and in each period, it's annual 6% interest, but in a quarterly period, it's only 1.5. And monthly compounding, now the year is divided into 12 monthly compounding periods, and then after 1 month has gone by, at 6% annual interest, it's 0.5% of interest for that month. Okay, and then but you do that 12 times. Okay, and so when you crunch it out, multiply it out, you can actually see that you get a little bit more. Okay, so theoretically, you might ask the question, well, so what's going on, right? So here, the factor here it starts, the factor starts at 1.06, and then you kind of chop the interest rate in half so it becomes 1.03. You chop that interest rate in half so it becomes 1.015. You chop that one again, you know, in thirds, right? So now the compounding factor is even smaller, but there's more of them, right? And so as this factor gets closer and closer to 1, you know, raising anything to the, you know, raising 1 to any power is still 1, right? So it kind of like sort of decreases its strength to make it bigger, right? Because the factor itself is getting closer to 1. So, you know, you might say, it's becoming weaker. On the other hand, you're having more of them, right? And so it turns out that in the end, it does have some effect. But you might consider, you know, what happens if we did it, you know, continuously? What would happen, right? So as this rate, I divided by C, becomes smaller, that tends to make the total rate less. However, the exponent C is more terms in the product, and so when you multiply more things that are larger than 1, that makes it larger. So which effect dominates, right? Because by dividing it by C, you're making it smaller, but by multiplying by more terms, by including more terms that you multiply, it could make it bigger. So which effect dominates? So it turns out that there's this relationship where the exponential function, e to the x, is actually this the result of this limit. And so if you look at this limit, that's exactly what we want, where x you know, is kind of constant, but as n is getting larger, you're doing exactly this. You're getting that smaller part smaller, but and n is the number of terms that you're raising it to, or times that you're multiplying it by, is getting larger. And so if you plug this in, you can see that it's basically e to the I. So this is one of those things where, you know, you can sort of forget this derivation a little bit and just remember this result. So this is like a Q is equal to the fixed cost divided by P minus the variable cost. So if you could just remember this, and it's so basically you just take the annual percentage and you raise it to the e power, and that gives you the continuous compounding. And so you can see that it's 1.0618. And so you can see how the biggest change, the biggest delta, is when you go from annual compounding to semi-annual compounding. When you go to quarterly compounding, quarterly is more than semi-annual, but not that much more. When you jump to monthly compounding, it's more, right? But it's not that much more, right? And then finally, when you go to continuous compounding is the most. It's the highest, but it's not that much more than monthly. Does that make sense? Yeah. So if you ever want to know in other words, if you didn't have, you know, if you wanted to very, very quickly estimate, you know, what monthly compounding is, you could just take the annual interest rate and raise it to E, and then you get this, you know, 1.06. And so this is wrong. I mean, this is continuous compounding. It's not monthly compounding, but it's kind of a quick way to get an estimate, an upper bound, say. The monthly compounding will not be greater. None of the other, like quarterly or semi-annual, none of them will be greater than the continuous compounding. So it's kind of an upper bound estimate. Okay. So let's see. Data table. We want to say something very quick about the effective interest rate first. So the effective rate basically is if we left some funds in deposit for 1 year, what would we have at the end? Okay, and so it turns out that, and so here's some examples on effective interest rate, which are a little bit tricky, but it turns out that there is this what's called the I-conv, or kind of like the interest conversion worksheet on the calculator. Okay, and so basically you will put in, say, what's called a nominal interest rate, and then you get back the effective rate. Okay, so let's take a look at that. So it's the iconv, which is above 2. Okay, so if you do second 2, you get the worksheet, and so let's actually clear the worksheet. So the clear worksheet is up above the base. This is the main clear button on the calculator. So we do second clear, we clear the worksheet. So nominal interest rate, that's kind of like the annual interest rate, so we enter that. And then the next one is what's the effective rate, effective interest rate. And so here, this is the compounding periods per year. And so if we put in 2, enter, we can go down and we can see, let's compute the effective rate. So that's 6.09, right, which is what we had before, right? Then if we wanted to see what quarterly compounding is, we do 4 and enter. Okay, now when we go back to nominal, it's still 6%. And here, this is the old leftover one from the previous set of values. And so when we compute, we get the star up there. And it's the 6.14, right, which is basically this rate that we saw before. And so to find the effective rate for monthly compounding, right, we can change the number of compounding periods per year to 12. So now it's monthly. And then the nominal rate is 6%. And the effective rate is, oh, sorry, not enter. Let's see if we can compute that, 1.67, yeah. So if we have 12 monthly compounding, 6%, that's the computed effective interest rate, which is 6.17%, right, rounded. Okay, so the sort of the long way to do it without using the calculator is to basically say, here's my compounding, right? So here's my annual nominal rate, and this is the number of compounding periods per year, and I'm going to raise it to the number. That's basically what we have, right? And so this R is the effective rate after 1 year. And so if you just sort of punch those out, you would get the effective rate. Okay, and so the effective rate helps you compare interest rates. And so here, this is a sort of a different type of a problem where it's telling you the effective rate, and it's telling you this effective rate, and you want to go back and find what is the nominal rate. And so it involves logarithms. So sometimes you might see those problems. But in the calculator, it's actually quite easy, because you would just say, put in the given nominal rate, you put in the compounding, and then you would actually just compute the nominal rate. And then the calculator does all of that logarithm stuff for you. Okay, let's see. Oh, basically, let me just briefly set this problem up, right? So suppose your firm is considering 2 projects. Project A will pay 1,000 at the end of 5 years. If your interest rate is 6% compounded quarterly, which should you use? So again, let's just set it up, right? So with these TVM problems, you always start out, or I would like you to think about always starting out with N, I, PV, PV, PMT, and FV, right? So we'll pay 1,000 at the end of 5 years, so this would be 1,000, right? So there's no annuity yet, and then we want to compute the present value. And so here we're looking at 5 years, and the rate of interest is 6%. But now we're told that it's compounded quarterly. So what we have to do is we add the second row to the TVM table, which is 4. So now, instead of 5 annual periods, if it's quarterly compounding, how many compounding periods are we dealing with? 20. Good, thanks. Okay. And if the annual rate is 4%, sorry, 6% interest, and we have quarterly compounding, what's the interest rate within each period? Oh, sorry. The interest rate within each period is 6% divided by 4, right, which is 1.5%. Does that make sense? So to get this on the calculator, you would just do clear TVM, and then for the number of periods, you put in 20. Okay, and then for the interest rate, you don't put in 6, right, because it's 6% compounded quarterly, so you put in this 1.5%. Okay, and so we're talking at 1,000 is going to pay 1,000 at the end, and so you compute the present value. Oh, sorry. I think I messed up something. So let's put in 1,000. Let's try that 1,000. Oops, 10,000, 1,000. Future value, and so let's compute the present value. Wait. No, I'm messing something up. Right. So let's second quit out of this worksheet. Okay. So let's clear TVM. Okay. So let's do 20 time periods. And then the interest rate is not 6%, 6% annually, compounded quarterly, so we divide it by 4. We put in 1,000 for the future value, and we want to compute the present value. Okay? And then for B, again, it's sort of quarterly, but it's for 7 years, right? So it would be 28. And it's still the same 1.5%, right? So, and it's a different FV. So if we update the FV to 1120 and put that in for FV, and we change the number of years from 20 to 28, then we can compute. Oh, I think I was doing second, right? I can compute the PV, and then we get this value. Okay, so when you start to have compounding, remember the first row is always the annual year, always the annual row where you collect the data. But then when you do the quarterly or semi-annual or monthly compounding, that's when you build up your second row. And so this helps you to remember that the number of periods is not 5 annual periods, but it's 20 of these quarterly periods. And if the annual interest rate is 6%, then the actual rate in the period is a quarter of that. So you divide that by 4. Does that make sense? So that's how you use those. And then you input these numbers into the calculator, your present value function, or the lookup tables for the present value factors. Okay? So see you tomorrow, and we'll do annuities next. PMT. Yes. Sorry?
I came 10 minutes late.
Okay.
The parking meter was...
no problem. You're...
Eric Wallace?
Eric Wallace. Okay, got it.
Okay. And are you work tomorrow? I'm not going to be coming into
Oh,
class.
right.
Okay.
Yeah. So there, I will email you instructions on how you can view the lecture.
I'm going to be gone, like, off island.
Okay.
So,
yeah, as long as you...
on, like, Monday?
Yeah.
Okay.
That's fine, that's fine.
Okay, awesome.
There will be homework due on Monday. So do you need an extension then for that homework?
I could probably do it on Sunday. But I won't have a computer on Friday or Saturday.
Okay.
So,
Yeah. So
if I do need one, I'll email you, but I probably shouldn't.
Okay.
So maybe we'll take care of it.
Okay.
So it'll be homework.
And then on Monday, class will be over in the lab, E102.
Oh, Monday's the
Monday.
last day.
Monday. Right.
Okay.
Right. So you're fine.
Okay, perfect. Thank you.
And then Monday over there.
Excellent.
Okay.
Oh, last question.
Okay.
All right. So for the question number 2 on our homework, like I ended up with a 1.15.